Welcome to your Easter work. We're going to start off by finishing off the equilibrium topic, and we're going to start on page 10. So we've discussed these effects in great detail in class, and page 10 provides a helpful summary of the effects of the changes in concentration, pressure, temperature and catalyst on a system in equilibrium, and it provides helpful frameworks for writing these explanations in exam questions. So you should always include in your answers, if I just write this up at the top here, you should always include in your answers the side the equilibrium shifts to. So that's your left hand side, your right hand side. You should explain why that happens. So be that because the forward reaction is exothermic, or there's fewer moles of gas on one side if you're talking about pressure changes. And always then just finish off your explanation by stating that that happens to minimise or oppose the change that the system has been subjected to. So when you're starting to practice writing these explanations, have page 10 here in front of you and use that as your framework of explaining, making sure you include all those details, what side it shifts to, or if the question has asked you about yield, make sure you say whether the yield increases or decreases. Make sure you've explained why and say that that's to minimise or oppose change, and that's all according to Le Chatelier's principle. So I think it would be worthwhile at this point just stopping and having a go at some of the explanation questions. You have a booklet of questions that says past paper questions on 2.9 and 2.10. Even question 1 there, you would be able to answer question 1 part A to D at this point, and it asks you to explain effects of pressure, temperature, catalyst and so on the system. So it would be worth having a go at those now. I don't have those questions imported in to this presentation, but I'll do question 1 part B with you. So I've written the equation, and again this is past paper questions on 2.9 and 2.10, the booklet of questions I gave you. So this is the equation for question 1. You can see nitrogen monoxide reacting with oxygen to give you nitrogen dioxide, and you're given the enthalpy change for that reaction. Delta H equals minus 116 kilojoules per mole. So we can tell from that the forward reaction is exothermic, and that means the backward reaction is endothermic, and that will come into part C. But if we look at part B first of all, just have a look at what these explanations would look like. Also have page 10 of your equilibrium booklet out in front of you, because we'll follow that framework of answering. So look at page 10 there and look at the pressure section. It says state the number of moles of gas on each side. Okay, so we're going to start our explanation by simply saying there are 3 moles of gas on the left hand side, and you can see there are 2 moles of gas on the right hand side. Okay, so that's following the first point of our framework. It then says state which side the position of equilibrium will move towards. So we're saying which way is it going to go? Is it going to go right or left? Well, look at your question in part B. It asks you to explain how increasing the pressure will affect the equilibrium yield of nitrogen dioxide. So we know the direction it's going to move. It's going to move to the right hand side because there are fewer moles of gas. But the question asks you about the equilibrium yield. So what we can actually do, you can just say that it will increase the equilibrium yield, but you can make the point that it will shift to the right hand side, therefore increasing the yield. So we might do that for a full explanation. So the equilibrium position will shift to the right hand side And then we need to, because the question has asked me about the yield, we need to make that point that it increases the yield. So equilibrium position will shift to the right hand side, increasing the yield. Okay, then we want to explain why. And why this happens is since an increase in pressure favours the side with fewer moles of gas. Or you can say with a smaller volume, because we know that fewer moles of gas means a smaller volume, since 1 mole of any gas occupies the same volume. So therefore we've got 3 volumes on the left and 2 volumes on the right. And we just want to finish that off by saying this happens to minimise the change. Minimise or oppose the change. So let's read through our answers. We've said, first of all, stated following our framework to explain the number of moles of gas on each side. So there are 3 moles of gas on the left hand side and 2 moles of gas on the right hand side. The equilibrium position will shift to the right hand side, increasing the yield, since an increase in pressure favours the side with fewer moles of gas to minimise the change. So we've stated how many moles of gas on each side. We've said which way it will go, what effect that has on the yield, and explained it in terms of increase in pressure, moving to the side with fewer moles of gas, and then finished off our explanation with simply saying this all happens to minimise or oppose the change, and that's in line with Le Chatelier's principle. Okay, so for each of your explanations, make sure you state which side it goes, explain fully why, and say that it happens in order to minimise the change. So once you've had a go at practising some of those explanations, we'll have a look at this idea of equilibrium constants. Equilibrium constants essentially give us an idea of how far the equilibrium lies to the right or to the left. So if the equilibrium constant had a value of much greater than 1, then it would indicate that the equilibrium position lies further to the right. If it was much less than 1, it indicates that it would lie further to the left. So it's all this idea of ratio, and we'll have a look at how Kc or your equilibrium constant is expressed in just a minute. Now there are different equilibrium constants. You can have equilibrium constants with respect to concentration, with respect to pressure, with respect to acid dissociation, with respect to separation between different solvents. So there's plenty of equilibrium constants, but we're just going to look at Kc this year, which is the equilibrium constant with respect to concentration. And actually at this stage in AS, all you need to be able to do is write an expression for Kc for a particular reaction or equation, and be able to work out the units that Kc would have. You actually don't need to be able to work out a mathematical value. So this bit underneath where it introduces Kc just goes over that idea again of it giving us an idea of how far to the left or right the equilibrium sits, and gives you some values there of greater than 1 or less than 1. But this is what's really important down here, is the expression for Kc. So we've got a reaction, A plus B, reacting to give us C plus D, and the expression for Kc written underneath. So essentially what we have is at the top of our fraction, if I just zoom in here, the top of our fraction, we have the concentration of our products. So those are our products, C and D. The letters C and D in square brackets represent the concentration of C and D. So it's the concentration of C, let's just focus on this one now. The concentration of C raised to the power of C. That C is supposed to be a small c, and it's raised to the power of its balancing number essentially. These small letters, A, B, C and D are the balancing numbers of the reactants and the products. So it's the concentration of our first reactant raised to the power of its balancing number. Then the concentration of our second reactant raised to its balancing number. And that is all over the concentration of our reactants to the power of their balancing numbers. So we separate it all out. So essentially what we've got is the concentration of our products to the power of their balancing number over the concentration of the reactants to the power of their balancing numbers. So let's look at a real equation to see if we can write this expression for Kc. So over on the next page, let's look at example 1. We've got a simple reaction here, PCl5 reacting to give us, it's really decomposing to give us PCl3 plus Cl2. So let's write an expression for Kc, the equilibrium constant with respect to concentration. So Kc is, and then we remember it's a concentration of our products over concentration of our reactants. So let's take the first product here. It's PCl3. How I represent the concentration is I put the formula in square brackets, not round brackets, square brackets. Okay, and we said that was raised to the power of its balancing number. Now the balancing number in front of PCl3 is essentially 1, but we know that anything raised to the power of 1 is just itself. So actually where there's no balancing number, we don't need to include that 1. Okay, then it's multiplied by the concentration of our next product, which is Cl2. So it's a concentration of Cl2, and that's all going to be over the concentration of our reactants raised to their balancing number. So again, we've got PCl5 here, but no balancing number in front. So I don't need to put it to the power of anything. And that's simply your answer. Let's move on to example 2, where you do have balancing numbers this time. So Kc is equal to the concentration of our products, first of all, on the top half of our fraction. So we've got ammonia here. So we'll write the concentration of ammonia, NH3, in square brackets. But we've got to include the power of our balancing number. So you can see the balancing number is 2, so it's concentration of NH3 squared over, then we go to the concentration of our reactants. Our first reactant is nitrogen, and you can see it has no balancing number, so there's no power after the concentration of nitrogen. Our next reactant is hydrogen, so we multiply it by the concentration of our hydrogen, H2, and we raise that to the power of the balancing number, which in this case is 3. Have a go at doing example 3 and 4. So pause the video, try writing those yourself, and then I'll go through them to check. So example 3 is your expression for Kc should have been written as Kc is the concentration of NO2 squared, because the balancing number is 2, over the concentration of N2O4 with no power because there's no balancing number there. Simple as that. And then for example 4, we've got Kc is equal to concentration of our product, well our only product is sulfur trioxide, SO3, to the power of its balancing number. Its balancing number is 2, so it's SO3 squared over concentration of our reactants. First reactant is sulfur dioxide, but it has a balancing number of 2, so we've got to put that to the power of 2, so SO2 squared, times by the concentration of our oxygen. No balancing number in front of the oxygen, so I don't need to include a power. The other thing you might be asked to do in terms of Kc is work out the units of Kc for a given equation, although at this stage you don't need to work out the value, but they may ask you about the units. And because we have different equations with different number of moles of reactants and products, actually the units of Kc will change from equation to equation. So we need to think first of all, Kc is written in terms of concentrations. What is our unit of concentration? It's moles per decimeter cubed. So each of our concentration values within our Kc expression will be written with the units of moles per decimeter cubed. The first thing, the easiest thing to do for this is actually to write your expression for Kc first of all. So let's look at example 1 here. Kc would be equal to, and I'm going to do these all in different colours for our units later on. It's going to be the concentration of hydrogen, because that's our first product, and it's going to be squared because there's a balancing number of 2 in front there. That's going to be multiplied by the concentration of sulphur, and again that's going to be squared because of the balancing number. Then we have the concentration of our reactants on the bottom of our fraction. So it's concentration of hydrogen sulfide, and again that's going to be squared because of the balancing number of 2 in front. Okay, so our expression for Kc has been written, and now we need to think about the units of these individual components of concentration. So, say for example the concentration of my hydrogen would be 2 moles per decimeter cubed. Okay, the units of the concentration of hydrogen is moles per decimeter cubed. Don't need to worry too much about the value of that for now. But because the concentration is squared, I'm also going to have to square my units. It's going to be the same story for sulphur. The concentration will be given in moles per decimeter cubed, but I'm squaring that value, so I have to square the units as well. That's all over the concentration of hydrogen sulfide squared. Again, the units of hydrogen sulfide concentration is going to be moles per decimeter cubed, but that's going to be squared. Now there's different ways of moving forward at this point. If I looked at this particular example, I would probably see that my moles per decimeter cubed squared on the bottom would cancel out with one of these brackets, because they're both moles per decimeter cubed in the brackets and squared on the outside of the bracket. That would be me left with moles per decimeter cubed in the brackets to the power of 2. And then when we're multiplying out powers within a bracket, that would be technically moles to the power 1 times by 2 on the outside, which is moles squared, and then decimeters to the minus 3 times by 2, which is minus 6. So your units would be moles squared to the dm minus 6. So that's one way of doing it. Another way of doing it is by, let's go back to this stage, is by adding the powers on your the top part of your equation and then separately on the bottom. So if we give ourselves a bit of room again. So you can see that inside my brackets I have the same unit, I have moles per decimeter cubed. So the rules of indices state that when we multiply things with powers, we add those powers, we add those indices. So for example, if you were doing x squared times by x cubed, you would get x to the power 5. So if you treat moles per decimeter cubed as your x, we've got x squared times by x squared, which is going to be x to the power 4. So my units on the top, hopefully this is not getting too complicated, it's going to be moles per decimeter cubed to the power 4 divided by, we can't simplify the bottom, so it's moles to the decimeter cubed to the power of 2. Okay, back to your rules of indices for a second. Let's say this time I had x to the power 5 over x squared. The rules of indices state that when you're dividing, you minus your indices. So x to the power 5 to x over x squared is really equal to x 5 minus 2, which is x cubed. So here what we're doing is we're minusing the powers. So we're doing moles to the decimeter cubed to the power 4 and 4 minus 2, because we're dividing by moles to the decimeter cubed squared. A lot of squared and cubed in here, so hopefully you're following along. So that's going to be equal to moles to the decimeter cubed squared. Again, if we multiply out that bracket, we can see that it's moles squared times by dm to the minus 6. So we get the same unit whatever way we do it. One other way of doing that, and that goes way back just to looking at our equation. So if I just move this over, obviously you might be running out of room by this stage, but if we have a look at our equation, how we can do this is simply by, and this is represented just above in your general equation here, we can simply do that our units are going to be moles times dm to the minus 3 to the power c plus d. What we mean by that is the total balancing numbers of our products. And that's all going to be over moles per decimeter cubed to the power of the total balancing numbers of our reactants. So it's total balancing numbers of reactants. Okay, so what that means is that if I find a wee bit of room here, if we're looking at my equation here, we've got the units of Kc are going to be, and if I actually move up a wee bit so you can see that general equation again, it's going to be moles per decimeter cubed to the power of C plus D. That's the total of our balancing number of our products. So we've got 2 in front of our hydrogen and 2 in front of our sulfur. So the total balancing number is going to be 4 over moles per decimeter cubed to the power of the total of our balancing number of our reactants. So again, if we look at that, we've only got one reactant and its balancing number is 2. So we've got moles per decimeter cubed to the power 4 over moles per decimeter cubed to the power 2. And from that point, we proceed to say that then it's going to be moles per decimeter cubed to the power of 4 minus 2. 4 minus 2 is 2. So it's going to be moles per decimeter cubed to the power 2. Multiply that out, you get moles squared dm to the minus 6. Essentially, we could simplify that even more to say that essentially what we're doing is moles per decimeter cubed, don't know what colour to go for now, C plus D minus A plus B. That's what we end up doing. See how we ended up doing 4, which was the total balancing number of our products, minus A plus B, the total balancing numbers of our reactants. That ended up being our power. So technically speaking, let's see where we could write that. If you've any room beside this equation up here, your general equation. So that's essentially equal to moles per decimeter cubed to the power of C plus D minus A plus B. Now that might look really confusing, but actually what I'm just saying, and we'll maybe put that in brackets as well, what we're saying is if you can work out the total balancing number of your products minus the total balancing number of your reactants, that will be the power to which your moles per decimeter cubed is raised to. So loads of options there. You might need to go through all of them again to fully figure them out. It will totally vary which one you prefer to do. If you're happy enough with the powers of indices, you might be happy enough with that final simplification there. If you're not too sure about it, you might want to take a step back and use this. Or if you'd prefer to look from example to example, you could do it how I first did it, writing your Kc expression, and maybe looking to see how you can cancel out. So I'll do the next one with you, and then maybe you could try the next one on your own, whatever way you would prefer to do it. Or even at this stage, if you're happy enough to pause, try it your way and then see if you get the final answer, because how I do it may be different than how you choose to do it. So let's look at example 2 here. So let's write, I'm going to write an expression for Kc anyway. So Kc is going to equal, we've got the concentration of our hydrogen iodide. That's to the power of 2, because there's 2 moles of hydrogen iodide. That's going to be over your concentration of hydrogen, H2. No balancing number needed there, because there's no balancing number in front of the hydrogen. And then that's going to be multiplied by the concentration of your iodine. And again, no power needed because there's no balancing number. So again, if we substitute in the units of concentration, where we have a term for concentration, so the unit of concentration of hydrogen iodide is going to be moles per decimeter cubed. But we're squaring that value, so that means we need to square the units as well. That's going to be over hydrogen is going to be in moles per decimeter cubed, and so is iodine, moles per decimeter cubed, and no powers needed on the bottom half because there's no balancing numbers in our equation for the reactants. So we can't directly cancel anything out in this equation because we've got squared on the top and there's nothing, none of our terms are squared on the bottom. So I would maybe simplify that down to us having moles per decimeter cubed to the power of 2 on the top, divided by, essentially these have indices of 1. So when we're simplifying this down, it's going to be 1 plus 1, which is 2, when we're multiplying our terms. Again, that's just like saying x times by x, which is obviously going to be x squared. So we're going to have moles per decimeter cubed to the power of 2 on our bottom half as well. And what we can see from this example is that we have moles per decimeter cubed squared on the top and the same on the bottom as well. So actually these terms of units of concentration cancel out. And so for this equation, Kc has no units. But in the exam, you would have to state that and say next year when we come to calculate values for Kc, you would give your value and then at the end you would state no units. And that's really important to do so that the examiner knows you haven't just left them out, but you've actually worked it out and found out that Kc is going to have no units because you have moles per decimeter cubed squared on the top and moles per decimeter cubed squared on the bottom. So in this particular example, you have Kc has no units. Again, if we were doing that the slightly simpler way, we would be saying, okay, my units are going to equal moles per decimeter cubed to the power of my products, or the balancing number of my products, which is 2, divided by moles per decimeter cubed to the power of the total of my balancing number of my reactants. If I go back to my equation here, I can see that balancing number of hydrogen is 1, balancing number of iodine is 1, so the total of that, 1 plus 1, is going to equal 2. So it's possibly a slightly easier way to do it. If you're thinking at this stage about minusing your indices, again, you can do it that way. So what we're saying is it's going to be moles per decimeter cubed to the power of 2 minus 2. I'll maybe even write that out in full in this example. Moles per decimeter cubed to the power of 2 minus 2. 2 minus 2 is obviously 0. Anything to the power 0 is equal to 1. So essentially if you had a value of Kc coming out as 25. It'll be 25 times by 1, which is obviously 25. So there's no units. So it doesn't really matter which way you do it. But you should always get the same final answer. Okay, why don't you give number 3 a go, whatever way you'd prefer to do it, and then check the video to check that you've done it correctly. Okay, we'll start with the quickest way this time, and that is by just saying that the units are going to equal moles per decimeter cubed to the power of our total balancing number of our products. There's only one product here and its balancing number is 2. So it's going to be moles per decimeter cubed to the power of 2. That's going to all be over moles per decimeter cubed to the power of the total balancing number of our reactants. Balancing number of nitrogen is 1, balancing number of hydrogen is 3. Total of those is going to be 4. Okay, so at this point, we're saying that it is moles per decimeter cubed to the power of 2 minus 4. Got to be careful at this point. That gives you moles per decimeter cubed to the power minus 2. At this stage, we need to multiply out our powers. So we've got moles technically to the power 1, and then dm to the power minus 3. So let's separate that out. We've got moles to the power 1 times by minus 2. So that's moles to the minus 2. Then we've got decimeters to the minus 3 times by minus 2. Minus 3 times by minus 2 is 6. So it's actually moles to the minus 2 decimeter to the power 6. So that's a little bit complicated. You need to remember your rules for indices, that where we're multiplying outside, or the powers outside the bracket, we multiply the powers on the inside of the brackets. And then also we've got some negative powers going on there. So it's moles to the minus 2, and then decimeters you're doing minus 3 times by minus 2 outside the brackets, which gives you a power of 6 for your decimeters. The slightly longer way of doing that, although you should get to the same point, would be writing your expression for Kc. So Kc is going to equal concentration of ammonia squared over the concentration of nitrogen times by the concentration of hydrogen cubed. So that would be moles per decimeter cubed to the power of 2 for your ammonia, moles per decimeter cubed for your nitrogen times by moles per decimeter cubed to the power of 3 for your hydrogen. That's going to work out again then as moles per decimeter cubed to the power of 2. Adding your powers on the bottom, moles per decimeter cubed to the power of 4, and then we end up back here in order to work out our final unit. Or again, the very simplest way of doing it is by taking your units of moles per decimeter cubed, putting it in brackets, and saying that the power of this that I multiply it by is going to be the total balancing numbers of my products, which is 2 in this case, minus the total power of the balancing number of my reactants, which is 4 in this case. 2 minus 4 is obviously minus 2. Then we multiply it out. So this way is probably the simplest, if you can remember that your units are going to be moles per decimeter cubed to the power of balancing number of products minus balancing number of reactants. So loads of ways to do that. Hopefully I haven't overcomplicated it by giving you all the methods, but find the method that suits you best and that you're best able to work through. Now, I think what you should do at this point is to stop and to have a look at the other set of equilibrium questions, the one that says equilibrium 1 at the top. So your separate booklet of equilibrium questions, equilibrium 1. But actually, rather than doing equilibrium 1 first, at this point the relevant questions would be your equilibrium 3. And that looks at KC expressions. What it asks you to do for each case is to write KC, looking from question 4 there, goes 1, 2 and then question 4, is to write an expression of KC and state the unit. So the first, question 4, first question is 2 HBr, giving you H2 plus Br2. Kc is going to equal the concentration of hydrogen times by the concentration of bromine all over concentration of hydrogen bromide to the power of 2, because the balancing number of hydrogen bromide is 2. So that's your expression for Kc. Move all this up. Your units, again, quickest way of doing it is going to be moles per decimeter cubed to the power of your total balancing number of your products. So it's going to be 1 plus 1 is 2 minus the total balancing number of your reactants, which is 2 in this case. 2 minus 2 is 0. So it's going to be moles per decimeter cubed to the power of 0. And we know that anything to the power of 0 is just 1. And in other words, there's no units. And where there's no units, you need to state the words no units rather than just not writing anything. And we can see how that works out. The reason why it works out that there's no units is because the total balancing number on the left-hand side of your equation is equal to the total balancing number on the right-hand side of your equation. So where you have that scenario where there's the same number of moles on each side of the equation, your Kc expression is always going to equal no units. So that might save you the working out if you were to learn that or become familiar with that. You will become familiar with it due to practice, but it's worthwhile stating it at this point. So if the moles on the left hand side equals the moles on the right hand side, then Kc will have no units. You still need to write an expression for Kc, but Kc is not going to have any units. So have a go at that equilibrium 3 sheet before you move on to the next section. Okay, we're getting there. So now that we have looked at writing expressions for Kc and finding units for Kc, specification also requires us to look at the effect of changes in our conditions on the value of Kc. And the key thing to remember is that equilibrium constants for Kc are only constant at a constant temperature, at a given temperature. So Kc changes with temperature. That's one thing to remember. But the other thing to remember is that any other factor, pressure, concentration, catalyst doesn't even affect the position of the equilibrium, but in particular learn that pressure or concentration don't affect the value of the equilibrium constant. So in other words, Kc is not affected by changes in pressure or concentration, but Kc is affected by temperature. Okay, so you can see that in the box here. So you can see that Kc is only affected by changes in temperature. So changes in temperature mean the value of Kc is affected, but change in pressure or concentration, the equilibrium will shift, the position will be affected, but the value is not affected. Now it's important not to get this mixed up with your position of your equilibrium, because remember we have studied the effects of temperature and pressure on the position of the equilibrium. So position of equilibrium is affected by concentration, temperature and pressure, but the value is only affected by temperature. Okay, so when you're asked about the position of the equilibrium, that goes back to the start of this topic of looking at the different factors, whether it's going to go left or right. But when you're asked about the value, it's only temperature that changes the value of Kc. So value of Kc affected by temperature, position affected by concentration, temperature and pressure. Now, they will try to trick you up in this in the exam. Yes, it will affect the position of the equilibrium, that's changes in pressure and concentration, but they won't have an effect on the value of Kc. It's only affected by temperature. Value of Kc is only affected by temperature. If they ask you the effect of concentration or pressure, you need to simply say there's no effect on the value of Kc. Thank you for trying to trick me, but no, there is no effect on the value of Kc with concentration or pressure. Changing the temperature will, however, affect the value of Kc, and you need to be able to work out whether it increases or decreases the value of Kc. So let's have a look at the effect of the change in temperature. Essentially, what you need to be able to work out is the direction that your equilibrium shifts, and then the effect on the value. So the simplest thing to do is work out the direction. If it shifts to the right hand side, your value of Kc increases. If it shifts to the left hand side, your value of Kc decreases. Because remember, Kc is essentially products over reactants. Concentration of your products over the concentration of your reactants. Obviously we have to split them up and raise them to the power of their balancing number, but that's a simplified version of Kc. So if my equilibrium shifts to the right hand side, I'm going to be increasing the concentration of my products. It's on the top of my fraction, so my value of Kc is going to get bigger. But if I shift the equilibrium to the left hand side, the concentration of my reactants is going to increase, therefore lowering the value of Kc because it's on the bottom of your fraction. So we need to think about this in terms of exothermic and endothermic changes as well, to be able to work out what side, whether it's the right hand side or the left hand side, and then the value will depend on that. So let's look at the reaction, or the example of an exothermic reaction as an example to start with. So if my forward reaction is exothermic, that would be if delta H is negative, then my backwards reaction is going to be endothermic. We know that an increase in temperature favours the endothermic reaction. In this case, the endothermic reaction is the reverse reaction, the backwards reaction. So that means the position of the equilibrium is going to move to the left. We can also think of it as heat is a product of the forward reaction because it's an exothermic reaction. So if we increase the temperature, we're essentially increasing the concentration of heat. So the equilibrium shifts to the left to try and remove that heat and remove the excess heat. So if we're shifting to the left, let's go back up here. If we're shifting to the left, the value of Kc decreases. So Kc, the equilibrium concentration, the value will be lower. Take the same example, the same system. If we decrease the temperature, we're going to have the opposite effect, obviously. If we decrease the temperature, we're essentially lowering the concentration of heat. And we want to replace that then. So that will shift to the right hand side to replace the heat. So the equilibrium is going to move to the right. If the equilibrium position moves to the right hand side, the value of Kc increases, so it will be higher. Let's think about it now for an endothermic reaction. So if we had A plus B reacting to give us C plus D, and our enthalpy change was positive this time. That tells us that the forward reaction is endothermic. The backwards reaction is going to be exothermic. So it's the backwards reaction that gives out heat, so we can write plus heat on the left hand side. It's essentially a product of the reverse reaction or exothermic reaction. So in this case, if we increase the temperature, we know that favours the endothermic reaction, which in this case is the forward reaction. So the position of the equilibrium will move to the right, essentially trying to use up some of that heat which is on the left hand side. And the value of Kc is going to increase, so it's going to be higher once we increase the temperature. But for decreasing the temperature, we're essentially lowering our concentration of heat. We want to replace that. That happens by favouring the exothermic reaction, which will replace some of the heat of the system, which is the backwards reaction. So your equilibrium position this time is going to move to the left, and the value of Kc will be lower as a result. Over in the next page, that is summarised. So if you're asked to define or explain how an increase or decrease in temperature affects the value of Kc, you first of all, we've already talked about this, but the first step you need to do is determine whether it shifts to the left or right, remembering that an increase in temperature favours the endothermic reaction. And then from that, if it shifts to the right hand side, the value of Kc will increase. If it shifts to the left hand side, the value of Kc will decrease. Simple as that. And remember that if you're asked how a change in concentration or pressure affects your value of Kc, you say that it has no effect on the value of Kc. Yes, it affects the position, but no, it does not affect the value of Kc. So linked to step number 2 here is this next section, which allows us to predict whether a reaction is exothermic or endothermic based on a change in value of Kc. So what this question would look like is they would give you a value of Kc at one temperature and then a value of Kc at another temperature and ask you to predict whether it was exothermic or endothermic. So let's take this first bullet point as an example. So if in the question the temperature increases and also Kc increases, what can we tell from Kc increasing? We can tell that the equilibrium has shifted to the right. Okay, so equilibrium must have shifted to the right. What do we know about increases in temperature? They favour the endothermic reaction. So the forward reaction, because it's moving to the right, must be endothermic. But if the temperature increases and Kc decreases, what can we tell about Kc decreasing? Kc decreases, that must mean the equilibrium has shifted to the left. Increases in temperature favours the endothermic change. So the backwards reaction, the one that has caused the equilibrium to shift to the left, is endothermic. So the reverse reaction is endothermic. So the forward reaction must be exothermic. Now you might need to read over that again because this is a more complicated question that will require you to give a bit of thought to. But just follow that logic through. If Kc has increased, that must mean the equilibrium has shifted to the right. Then you can tell from that that your forward reaction must be endothermic. So the overall reaction is endothermic. However, if you've increased the temperature and it shifts to the left, that must mean that the backwards reaction is endothermic. So the forward reaction is exothermic. So below are some example questions. We'll have a look at question 1 in a second, but I want to fast forward to question 2 because that directly links to what we've just discussed about predicting whether a reaction is exothermic or endothermic based on changes in values of your Kc. So have a look at question 2 on the next page, page 17. It asks you to look at these various values for Kc and explain whether the reaction is endothermic or exothermic. So let's have a look at what's happening here. You can see that my temperature is in Kelvin, and as we go down the table, temperature is increasing. But what's happening to my value of Kc? Well, we can see that Kc is going from 1 times 10 to the 17 to 1 times 10 to the 4. So my value of Kc is actually decreasing. What does that tell me about the direction that my equilibrium is shifting to? Well, if Kc decreases, that must mean the equilibrium is shifting to the left-hand side. We know that increases of temperature, which is what I'm doing here, favours the endothermic reaction. So we can tell from that that the reverse reaction is endothermic, since it's moving to the left-hand side, which is the backwards reaction. The backwards reaction is endothermic, since an increase in temperature favours the endothermic reaction, which must then mean that the forward reaction is exothermic. So we would get our first mark in the question for stating that the reaction is exothermic. And if you had absolutely no clue, it's worthwhile just guessing the reaction is exothermic or endothermic, but you should be able to work it out. So the reaction is exothermic. Then we need to state what we have just worked out. So we need to state our trend first of all. So as temperature increases, the value of Kc decreases. What does this mean about the position of your equilibrium? This means that the equilibrium is shifting to the left-hand side. And what does that mean? Well, we know that increases in temperature favour the endothermic reaction, so the reverse reaction must be endothermic, and so the forward reaction is exothermic. Okay, it's a bit of a complicated explanation, but really what we're doing there is just talking through our thought process. So we said at the start that we can see the temperature increasing, and as it increases, Kc is decreasing, which must mean that the equilibrium is shifting to the left-hand side. We can tell from that that the reverse reaction is endothermic, because increases in temperature favour the endothermic reaction. So if the reverse reaction is endothermic, the forward reaction must be exothermic. So those sorts of questions do require a little bit of thought. So that's the only question you have of that type, but go back and do question 1 now to complete the booklet, and then I'll go through the answers afterwards. So pause the video, give question 1 a go, which looks at the effect of changing conditions on the position and on the value of Kc. Remember that the value of Kc is only affected by temperature. And then pause the video while you do that, and then I'll go over the answers. So first question back on page 16, question 1a, asks you to write an expression for Kc and determine its units. So Kc, we can see, is going to be the concentration of Hi, our product, squared, because it has a balancing number of 2, over the concentration of H2 times by the concentration of I2. In terms of units, again, a couple of ways of doing this. The simplest method is going to be by spotting that the number of moles on your right hand side is 2 moles. The number of moles on your left hand side is also 2 moles. And what we stated earlier was that if there are the same number of moles on either side of the equation, you're going to have no units. If we did it the long way, Hi is going to have a concentration of moles per decimeter cubed, but that's going to be squared, times by, over moles per decimeter cubed for hydrogen, times by mole per decimeter cubed for iodine. We can simplify that down to moles per decimeter cubed to the power of 2 over moles to the decimeter cubed to the power 2. Those cancel each other out to give us no units. But again, don't just write nothing. You need to write that it has no units. Part B then asks you the effect of doubling the concentration of hydrogen on the equilibrium position and also on the value of our equilibrium constant Kc. So let's look at the equation again. It's H2 plus I2 giving us 2Hi. Okay, so what the question is asking is, if we increase the concentration of hydrogen, what will happen to the position? Well, I'm increasing the concentration of a reactant. The equilibrium shifts to try and minimise that change. So it's going to shift to the right hand side to use up some of the extra hydrogen. So we can say that the equilibrium position shifts to the right hand side. If you were asked to explain that, it would be simply that you're increasing the concentration of a reactant. So the equilibrium shifts to the right to try and use up some of that extra reactant. Or basically just say that it is shifting to the right to minimise the change of increasing the concentration. Okay, then we also have to say the effect on the value of Kc. But remember that Kc, the value of Kc is only affected by temperature. So the value of Kc is not affected. Or just no effect on the value of Kc. Next question asks us to the effect on increasing the temperature on the equilibrium position and on Kc. Well, we need to go back to our equation again, and we can see that the enthalpy change is plus 104. We can tell from that that this is an endothermic reaction. So the forward reaction is endothermic, which means that the backwards reaction must be exothermic. That means I can write plus heat as essentially a product of the reverse reaction. So I can write it as a reactant on the left hand side. So if I increase the temperature, I'm increasing the concentration of my heat essentially. So it's going to shift to the right hand side to try and remove that heat. But also we know that increases in temperature favour the endothermic reaction, which is the forward reaction. Again, we don't need to explain that. We can just write simply that the equilibrium position shifts to the right. We know that happens because it favours the endothermic reaction. And then we have to comment on the effect of on the value of Kc. And we know that this time temperature does affect the value of Kc. So we can almost put a tick there and put an X beside the effect on the value of Kc when it comes to concentration. So because the equilibrium has shifted to the right, we know that that increases the value of Kc. So we would simply write value of Kc increases. At this point, you should have a go at the questions in your booklet that are entitled Equilibrium 4. That covers the effect of changes in conditions on your equilibrium position and the value of Kc. Big thing to remember, Kc, value of Kc, only affected by temperature. The position will be affected by concentration, temperature and pressure, but the value of Kc is only affected by temperature. So have a go at the Equilibrium 4 questions now before we move on to the last section of this topic. So the last section of this topic covers the compromise that has to be made in industry between the equilibrium of a reaction and the rate of a reaction. So the position of the equilibrium of a reaction will essentially affect your yield, but the reaction rate will determine how fast you get it. Okay, so if our equilibrium is good, then we'll have a high yield. If the rate's good, we'll get that at in a fast time. But if our equilibrium is low, then our value of Kc is low, then we'll get a low yield. But the rate might still be high, so we might get a low yield but at a fast rate. The opposite is also true. There could be a scenario where we have a high yield, so a large amount of product, but maybe a low rate, which means it would take us a long time to get that. In industry, we have to balance that. There has to be a compromise between the equilibrium and the rate, because sometimes we might change the conditions that might favour the equilibrium, but it would lower the rate, and vice versa. If we change the conditions, it might increase the rate, but it might have a big effect on the equilibrium and on your yield. So this is best looked at by some industrial examples. The first example we're going to look at is the Haber process. And that's making ammonia. You can see that this reaction is exothermic from the negative enthalpy change. So let's look at the effect of temperature first of all. So we've said that the forward reaction is exothermic. So that must mean that the backwards reaction, the reverse reaction, is endothermic. We know that an increase in temperature will increase the rate. But in terms of our equilibrium, an increase in temperature is going to shift the equilibrium to the left-hand side, because increase in temperature favours an endothermic reaction. So in other words, if I want to shift this equilibrium to the right, I'm going to have to decrease the temperature. So if we're looking at the equilibrium, it would be a low temperature that would increase the yield of ammonia. But actually, that's going to make the rate very slow. So at low temperature, the rate is too slow. Let's think about the condition of pressure as well. So we know that an increase in pressure favours the side with fewer moles. Well, let's look at what we have here. We have 4 moles on the left-hand side versus 2 moles on the right-hand side. So if we increase the pressure, that's going to move the equilibrium to the right-hand side, which will increase the yield. So a high yield of ammonia will be encouraged by a high pressure. But then with this, we need to think about the cost involved with a high pressure. So the higher pressure you have in your system, the more expensive it's going to be, because a high pressure requires a lot of energy. So we've got to have some sort of compromise here, and particularly in terms of the temperature. So we know that our yield is going to be increased by a low temperature, but that's going to slow the rate down a lot. So this is looking at your factors from unit 2.9, your kinetics, and this topic of equilibrium. So a low temperature will favour our yield, but the reaction is going to occur very slowly at a low temperature. So what we must do is come up with a compromise. The compromise is that we use a temperature of 450 degrees. So that's high, but not too high. And our compromise pressure is 200 atmospheres. We can see here that that gives us a 10% conversion. The unused gases are then recycled to give us a 95% conversion. So our compromise temperature is 450 degrees. And you would have learnt these conditions at GCSE. Your compromise pressure is 200 atmospheres. And your catalyst is an iron catalyst. Fe, or iron. So those are your compromise conditions. Reasonably high temperature, but not super high. Your catalyst of iron, and then a pressure of 200 atmospheres. So that is achieving a compromise between an acceptable yield and a reasonable rate. Second industrial example we're going to look at is the contact process, and again you're going to need to know the conditions for this and be able to explain it in terms of a compromise between yield and rate. So you're always thinking this is yield versus rate. Okay, and this is called the contact process, which is how we make sulfuric acid. What happens in this process is that we have sulfur burning in air, so reacting with oxygen to give us sulfur dioxide. That's then, your sulfur dioxide is then reacted with further oxygen to give us sulfur trioxide. Your sulfur trioxide is then dissolved in concentrated sulfuric acid to give something called oleum. Don't worry about the formula for it. And then water is added to that to give you more concentrated sulfuric acid. Now, so you don't need to worry too much about that process. What we're focused on here is the conditions for this process. So you can see from our enthalpy change that our forward reaction is exothermic, which means that our backwards reaction is endothermic. So again, we've got the same problem. My yield is actually going to be increased by a lower temperature, but that's going to make my rate very slow. So I'm going to need to come up with a compromise temperature. And then if we think of the effect of pressure, well, I need to count up my moles on either side of my equation. I've got 3 moles producing 2 moles. So we know that an increase in pressure is going to favour the side with fewer moles. So actually this is going to be favoured by, the yield is going to be favoured by a high pressure. So in terms of the equilibrium, our conditions should be low temperature and a high pressure. But particularly with the temperature, we've got the problem that the rate is going to be too slow. Rate is going to be too slow at low temperatures. Also, we've got a further problem in that sulfur dioxide. If we lower the temperature too much, sulfur dioxide, a gas, is going to liquefy. So we don't want that, and also the rate is too slow. If we want to increase the rate, we've got to increase the temperature, but that's going to shift the equilibrium position to the left hand side, which reduces the yield. So we've got to come up with a compromise. That compromise is a temperature of 450. So actually you can see these two processes, your temperature is the same. And that is also helped by this catalyst, which is vanadium 5 oxide. If we have a look at the formula of that, vanadium is, its symbol is V. And the V in brackets there is not for the symbol of vanadium. It's to show us that the valency of vanadium is 5. And we've got oxygen, which has a valency of 2. So its formula is V2O5. That's our catalyst, which means that actually even at a low pressure, we can achieve a pretty good yield of 95%. So actually, even though our equilibrium would be favoured by a high pressure, we talked earlier on about the problem of that being very expensive. And so this catalyst is so good that we only need to use a pressure of 2 atmospheres, and our conversion is still 95%. The other thing to note about this reaction is that because it's so exothermic, so it releases 197 kilojoules per mole of energy, that actually we don't need to heat it anymore to achieve this temperature of 450 degrees. So we don't need to heat it anymore. If I was to apply extra heat, my temperature would rise above 450 degrees because I'm applying extra heat and my reaction is generating extra heat, so it would go above that 450 degrees. So what happens is that the heat generated by the reaction is used to heat your incoming gases. So essentially the heat that's given out as a product of the reaction as such is recycled to heat your incoming reactant gases. And so no extra heat is needed. So because this reaction is exothermic, we don't need to apply extra heat. And because we use this catalyst of vanadium oxide, we only need to use a pressure of 2 atmospheres. So there's not too much extra energy being applied in this reaction. So you need to know your compromise conditions. With temperature, you're thinking again about this compromise between yield and rate. So the yield would dictate that you should do it at a low temperature. The rate would dictate that you need to do it at a high temperature. So in industry, we have to accept that there must be a compromise between these two. Compromise is that you do it at a temperature of 450 degrees, which means that you get an acceptable yield at a reasonable rate. So your temperature is 450 degrees C. Your pressure is 2 atmospheres. And your catalyst is vanadium 5 oxide, which is V2O5. And a point to note at this stage is that the compromise temperature, 450 degrees, is the same as the Haber process. Same as the Haber process. So you're only really learning one compromise temperature for both reactions, and that's because they are both exothermic reactions. So they are both, their yield is both favoured by a low temperature, like we've said here, but their rate is favoured by a high temperature. Therefore the compromise is the temperature of 450 degrees. The pressure for Haber is 200 atmospheres. For this it's 2. And then obviously your catalyst is going to be different for each. So you need to know your conditions for your Haber process and for your contact process, and understand that it's a compromise between yield and rate, particularly in terms of the temperature. Yield is increased by a low temperature, rate is increased by a high temperature, so we've got a compromise between the two. That is our topic of equilibrium finished at long last, and well done for sticking with it. You are now at the stage where you can answer all of the questions in those question booklets, both the one that starts with equilibrium 1. So you can finish off anything in that booklet, equilibrium 1, 2, 3 and 4. And then you can complete the questions that have past paper questions in 2.9 and 2.10 written at the top. Those are a mixture of questions between equilibrium and rate, and just when you're answering those, just make sure that you don't get mixed up between the effects of your concentration, pressure, temperature, catalyst on your equilibrium and on the rate. So think again, the idea of rate is how fast a reaction is happening. So make a couple of wee notes here. So when you're talking about rate, you're thinking how fast, and you're thinking about collision theory is how you're going to explain your answers. And then when you're thinking about equilibrium or your yield, you're thinking about left-hand side or right-hand side, and you're explaining that by Le Chatelier's principle, which states that a system will try to minimise, will shift either to the left or the right to minimise the change that the system has been subjected to. So don't get those explanations mixed up. Rate is collision theory, equilibrium is Le Chatelier's principle. So make sure that you're not mixing those two up. So you can answer all those questions now, and I'd encourage you to do so before you move on to your moles topic.